10th class students, we have finished periodic classification of elements. Now I am going to start you the chapter metallurgy. See, metallurgy mainly deals with metals, okay, but you should have an idea about non-metals also and how non-metals behaves with metals. So here I'm going to give you videos related to this chapter, principles of metallurgy, or in other terms it is simply referred as metallurgy, and sometimes you can name this chapter as metals and non-metals, okay, because metals individually they do not exist, so always they react with some type of non-metal to form oxides. Now I am going to give you the videos related to it. Do watch them. Here there are two videos which I will be repeating every week, okay, which covers the entire state syllabus of ours, okay, and my explanation will be given to you in the next week, wherein I'll be discussing all the question answers including the textbook part. So watch these videos very carefully and make sure that the digital content whatever you receive in physics of chapters, you just save them in your separate pen drive. Okay, students, so this is what what I want you to do is save those digital videos, so in future you will be needing these videos for quick revision. Thank you.
Principles of Metallurgy. Introduction. In class 8, you have studied about certain properties of metals like malleability, ductility, sonority, etc. Metals play an important role in our daily life. We use various metals for various purposes like gold and silver as jewelry, copper, iron, aluminium for making conducting wires and for making utensils, etc. We use many household articles made up of metals and their alloy at our home. Can you mention some articles that are made up of metals? Do metals exist in nature in the form same as that we use in our daily life? Have you ever heard the words like ore, minerals and metallurgy? Do you know how these metals are obtained? To understand these questions, we need to know about metallurgy. In this chapter, we discuss various concepts related to metallurgy and the process by which we are able to obtain the pure form of metal that we use in our daily life. Metallurgy is the process of extraction of metals from their ores. Human history in terms of materials had the Bronze Age and Iron Age. Pertaining to the metals, they started to use the bronze, an alloy of copper and tin, and iron. Now we have more than 75% metals among the elements available. How metals do occur in nature? The Earth's crust is a major source of metals. Seawater also contains some soluble salts such as sodium chloride and magnesium chloride, etc. Some metals like gold, silver, etc. and are available in nature in free state as they are least reactive. Other metals mostly are found in nature in the combined form due to their reactivity. The elements or compounds of the metals which occur in nature in the Earth's crust are called minerals. The minerals from which the metals are extracted without economical loss are called ores. Example, aluminum is the most common metal in the Earth's crust, occurring in most of minerals. However, it isn't economically feasible to extract it from most of these minerals. Instead, the usual ore from which it is profitable to extract is bauxite, which contains from 50 to 70% of aluminum oxide. Activity. Look at the following ores. Identify the metals present in each ore. Ore, Formulae, metal, ore, formulae, metal. Bauxite, Al2O3, 2H2O, Al. Copper iron pyrites, CuFeS2, Cu. Zinc blend, ZnS, Zn. Magnesite, MgCO3, Mg. Epsom salt, MgSO4, 7H2O, Mg. Horn silver, AgCl, Ag. Pyrrolite, MnO2, Mn. Hematite, Fe2O3, Fe. Zincite, ZnO, Zn. Rock salt, NaCl, Na. Cinnabar, HgS, Hg. Magentite, Fe3O4, Fe. Galena, PbS, Pb. Gypsum, CaSO4, 2H2O, Ca. Limestone, CaCO3, Ca. Carnallite, KCl, MgCl2, 6H2O, Mg. From the above table, we can get the metals are aluminium, copper, magnesium, silver, manganese, iron, zinc, sodium, mercury, lead, calcium. Now we will try to classify them as shown in the below table. Oxides, sulfides, chlorides, carbonates, sulfates. Bauxite, copper iron, horn silver, magnesite, Epsom salt. Pyrrolite, pyrites, rock salt, limestone, gypsum. Hematite, zinc blend, carnallite. Zincite, cinnabar, magnetite, galena. From the above table, we notice that ores of many metals are oxides and sulfides. Based on reactivity, we can arrange metals in descending order of their reactivity as shown below. K, Na, Ca, Mg, Al, high reactivity. Zn, Fe, Pb, Cu, moderate reactivity. Ag, Au, low reactivity. Extraction of metals from the ores. The extraction of a metal from its ore involves mainly three stages. They are concentration of dressing, extraction of crude metal, refining or purification of the metal. Ore, concentration of ore, extraction of crude metal from the ore by hand picking, washing, froth floating, magnetic separation. metals of high reactivity, metals of medium reactivity, metals of low reactivity, halides, oxides, carbonate ore, sulfide ore, calcination, roasting, electrolysis of molten ore, metal, reduction of metal, refining of metal, metals of low reactivity, sulfide ore, roasting, oxides, reduction, metal, refining, refining of metal, distillation, poling, liquefaction, electrolysis refining, chemical reduction, auto reduction, displacement method, electrolysis reduction, concentration of dressing of the ore. Generally, the ores are found mixed with earthy impurities like sand, clay, soil, etc. These unwanted impurities in the ore are called ganguage or matrix. The process of removal of ganguage from powdered ore is called concentration or ore dressing. Various physical methods are used to enrich the ore. The choice of method depends on the nature of the ore. Handpicking. If the ore particles and the impurities are different in one of these properties, like color, size, etc., using that property, the ore particles are handpicked, separating them from other impurities. Washing. Ore particles are crushed and kept on a sloppy surface. They are washed with controlled flow of water. Less dense impurities are carried away by water flow, leaving the more dense ore particles behind. Froth flotation. This method is mainly useful for sulfide ores which have no wetting property, whereas impurities get wetted. The ore with impurities is finely powdered and kept in water, taken in a floating cell. Air under pressure is blown to produce froth in water. Froth so produced takes the ore particles to the surface where the impurities settle at the bottom. Froth is separated and washed to get ore particles. Magnetic separation. If the ore impurity, the powdered ore, is dropped on the leather or brass conveyor belt, which moves over two rollers, one of these is magnetic. When the ore passes over the magnetic roller, it sticks to the belt due to the force of attraction and falls near to magnetic roller. The ganguage falls in a normal way under the influence of gravity. The magnetic ore and ganguage thus forms two separate heaps. Following figure shows the magnetic separation method. Reactivity of metals table. Metals, action of oxygen, reaction with cold water, reaction with steam, reaction with dilute strong acids, reaction with chlorine on heating. K, Na, Ca, Mg, Al, Zn, Fe, Pb, Cu, Hg, Ag, Pt, Au. Form Na2O, K2O in limited supply of O2 but form peroxides in excess of O2. Burn with decreasing vigor to form oxide CaO, MgO, Al2O3, ZnO, Fe2O3. Don't burn but only form a surface layer of oxide PbO, CuO, HgO. Don't burn or oxidize even on the surface. K to Mg displace H2 from cold water with decreasing reactivity. K violently but Mg very slowly. From Al to Au, do not displace H2 from cold water. K to Fe displace H2 with steam without decreasing reactivity. K very violent but Fe very slow. From Pb to Au, do not displace H2 from steam. K to Pb displace H2 from dilute strong acids with decreasing reactivity. K explosively, Mg very vigorously, Fe steadily, Pb very slowly. Cu to Au to not displace H2 from dilute strong acids. All metals react with chlorine on heating to form their respective chlorides, but with decreasing reactivity from top to bottom. This is understood from the heat evolved when the metal reacts with 1 mole of chlorine gas to form chloride. KCl, NaCl, CaCl2, MgCl2, Al2Cl3, ZnCl2, FeCl3, PbCl2, CuCl2, HgCl2, AgCl, PtCl3, and AuCl3 are formed. Extraction of crude metal from the ore. After concentration and dressing of ores that obtained from earth, we get an enriched ore. This enriched ore is to be converted into metallic oxide by reduction reaction. Then this metallic oxide is further reduced to get a metal with certain impurities. The reduction method depends on the position of the metal in activity serials. Metals of high reactivity. The metallic halides or metallic oxides of high reactivity metals are subjected to electrolysis to get the metal. Example, extraction of Na from NaCl. Fused NaCl is electrolyzed with steel cathode negative and graphite anode positive. The metal Na will be deposited at cathode and chloride is liberated at anode. At cathode, 2Na plus 2E minus gives 2Na. At anode, 2Cl minus gives Cl2 plus 2E minus. Moderately reactive metals. The ores of these metals are generally present as sulfides or carbonates in nature. Therefore, prior to reduction of ores of these metals, they must be converted into metal oxides. Sulfide ores are converted into oxides by heating them strongly in excess of air. This process is known as roasting. Generally, the sulfide ores are roasted to convert them into oxides before reducing them to metals. Example, 2 PbS plus 3 O2 gives 2 PbO plus 2 SO2. The metal oxides are then reduced to the corresponding metal by using suitable reduction agent such as carbon. Reduction of metal oxides with carbon. The oxides are reduced by coke in a closed furnace which gives the metal and carbon monoxide, CO. Example, PbO plus C at 1400 degrees Celsius gives Pb plus CO. Reduction of oxide ores with CO. Example, Fe2O3 plus 3CO gives in blast furnace 2Fe plus 3CO2. Auto reduction of sulfide ores. In the extraction of Cu from its sulfide ore, the ore is subjected partial roasting in air to give its oxide. 2Cu2S plus 3O2 gives 2Cu2O plus 2SO2. When the supply of air is stopped and the temperature is raised, the rest of the sulfide reacts with oxide and forms the metals and SO2. 2Cu2O plus Cu2S gives 6Cu plus 2SO2. Reduction of ores by more reactive metals. Thermite process involves the reaction of metal oxides with aluminium. When highly reactive metals such as sodium, calcium, aluminium, etc. are used as reducing agents. They display metals of lower reactivity from the compound. These displacement reactions are highly exothermic. The amount of heat evolved is so large that the metals produced are in molten state. Example, TiCl4 plus 2 Mg 850 degrees centigrades gives Ti plus 2 MgCl2. TiCl4 plus 4 Na 850 degrees centigrades gives Ti plus 4 NaCl. Low reactive metals. As they are less reactive, their ores are often found in free state. The oxides of these metals can be reduced to metals by heat alone and sometimes by displacement from their aqueous solution. When cinnabar HGS, which is an ore of mercury, heated in air, it is first converted into HgO, then reduced to mercury on further heating. Reaction: 2HgS plus 3O2 on heating, 2HgO plus 2SO2 heat gives 2HgO gives 2Hg plus O2. Purification of crude metal. The process of obtaining the pure metal from the impure metal is called refining of the metal. Some of the process of refining are distillation, boiling, liquefaction, electrolytic refining. The process that has to be adopted for purification of a given metal depends on the nature of the metal and its impurities. Distillation. This method is very useful for purification of low boiling metals like zinc and Hg containing high boiling metals as impurities. The extracted metal in the molten state is distilled to obtain the pure metal as distillate. Boiling. The molten metals is stirred with logs of green wood. The impurities are removed either as gases or they get oxidized and form some over the surface of the molten metal. Blister copper is purified by this method. Liquefaction. In this method, a low melting metal like tin can be made to flow on a sloped surface to separate it from high melting impurities. Electrolytic refining. In this method, the impure metal is made to act as anode. A strip of the same metals in pure form is used as cathode. They are put in a suitable electrolytic bath containing soluble salts of the same metals. The required metals get deposited on the cathode in the pure form. The metal constituting impurities goes as the anode mud. The reactions are: at anode, M gives Mn plus Ne. At cathode, Mn plus Ne gives M. Example: an impure copper is taken as anode and pure copper strips are taken as cathode. The electrolyte is an acidified solution of copper sulfide. As a result of electrolysis, copper in pure form is transferred from the anode to cathode. Reactions: at anode, Cu gives Cu2 plus 2E minus. At cathode, Cu2 plus 2E minus gives Cu. The soluble impurities go into the solution, whereas insoluble impurities from the blister copper deposited at the bottom of anode as anode mud, which contains antimony, selenium, tellurium, silver, gold, and platinum. Corrosion. The rusting of iron, tarnishing of silver, development of green coating on copper are some of the examples of corrosion. Corrosion is the deterioration of a metal as a result of chemical reaction between it and the surrounding environment. Do you know why corrosion occurs? Let us find. Experiment. Aim: to prove that the presence of air and water are essential for corrosion. Metals required: 3 test tubes, 3 iron nails, oil, water, and hot calcium chloride, rubber corks. Procedure: take 3 test tubes and place clean iron nails in each of them. Label the test tubes A, B, and C. Pour some water in test tube A and cork it. Pour boiled distilled water in test tube B and about 1 ml of oil and cork it. Put some anhydrous calcium chloride in test tube C and cork it. Leave these test tubes for a few days and then observe. After a few days, we will observe that iron nails rust in test tube A, but they do not rust in test tube B and C. Reason: in test tube A, the nails are exposed to air and water, hence the nails rusted. In test tube B, the nails are exposed only to water but not to air, because the oil floats on water and prevent the air from dissolving in water. Hence, nails are not rusted. In test tube C, the nails are exposed to dry air because anhydrous calcium chloride will absorb the moisture, if any, from the air. Hence, the nails are not rusted. From the above experiment, we can prove that air and water are essential for corrosion. Chemistry of corrosion. The chemistry of corrosion is quite complex, but it might be considered essentially as an electrochemical phenomenon. During corrosion at a particular spot on the surface of an object made of iron, oxidation takes place and that spot behaves as anode. We can write the reaction as anode 2Fe gives 2Fe 2 plus 4E minus. Electrons released at this anodic spot move through the metal and go to another spot on the metal and reduce oxygen at the spot in presence of H plus. This spot behaves as cathode with the reaction. Cathode O2 plus 4H plus 4E minus gives 2H2O. The overall reaction is 2Fe plus O2 plus 4H plus gives 2Fe2 plus 2H2O. The ferrous ions are further oxidized by atmospheric oxygen to ferric ions, which comes out as rust in the form of hydrated ferric oxide Fe2O3 XH2O, and with further production of hydrogen ions. Do you know, alloying is a method of improving the properties of a metal. We can get desired properties by this method. For example, iron is the most widely used metal, but it is never used in the pure state. This is because pure iron is very soft and stretches easily hot. But if it is mixed with a small amount of carbon, it becomes hard and strong. When iron is mixed with nickel and chromium, we get stainless steel, which will not rust. Pure gold, known as 24 karat gold, is very soft. It is therefore not suitable for making jewelry. It is alloyed with either silver or copper to make it hard. Generally, in India, 22 karat gold is used for making ornaments. It means that 22 parts of pure gold is alloyed with 2 parts of either silver or copper. Prevention of corrosion. One of the simplest methods of preventing corrosion is to prevent the surface of metallic object to come in contact with atmosphere. This can be done by covering the surface with painting or by some chemicals. Example, bisphenol. Another simple method is to cover the surface by other metals, SN, zinc, etc., that are inert or react themselves with atmosphere to save the object. This is generally done by electroplating. An electrochemical method is to provide a sacrificial electrode of another metal like Mg, Zn, etc., which corrodes itself but saves the object. Prevention of corrosion is of prime importance. It not only saves money but also helps in preventing accidents such as a bridge collapse or failure of a key component due to corrosion. A few important processes used in metallurgy. Smelting. Smelting is a pyrochemical process in which the ore is mixed with flux and fuel and strongly heated. The heat is so strong that the ore is reduced to even metal and the metal is obtained in the molten state. During smelting, impurities in the ore react with flux to form slag, which is removed. For hematite Fe2O3 ore, coke is used as fuel and limestone CaCO3 is used as flux. The smelting is carried out in a specially built furnace known as blast furnace. The reaction inside the furnace are 2CS fuel plus O2G gives 2COG. Fe2O3 hematite plus 3COG gives 2FeL plus 3CO2G. CaCO3S limestone flux gives CaOS lime plus CO2G. CaOS lime plus SiO2 silica gives CaSiO3 calcium silicate. Roasting. Roasting is a pyrochemical process in which the ore is heated in presence of oxygen and air below its melting point. The products obtained in the process are also produced in solid state. Generally, reverberatory furnace is used for roasting. Example, 2ZnS plus 3O2 gives 2ZnO plus 2SO2. Calcination. Calcination is a pyrochemical process in which the ore is heated in the absence of air. The ore gets generally decomposed in the process. Example, MgCO3 gives MgO plus CO2. CaCO3 gives CaO plus CO2. Flux. Flux is a substance added to the ore to remove the gangue from it by reacting with the gangue. If the impurity is acidic substance like SiO2, basic substance like COO is used as flux. If the impurity is of basic nature like FeO, acidic flux like SiO2 is added to the gangue. CaO plus SiO2 gives CaSiO3. FeOS plus SiO2 gives FeSiO3. Furnace. Furnace is the one which is used to carry out pyrochemical process in metallurgy. Furnace has mainly three parts. Hearth. Hearth is the place inside the ore is kept for heating. Chimney. Chimney is the outlet through which fuel, waste gases go out of the furnace. Firebox. Firebox is the part of the furnace where the fuel is kept for burning. Types of furnace. Blast furnace. Blast furnace has both firebox and hearth combined in big chamber which accommodate both ore and fuel. Reverberatory furnace. It has both firebox and hearth separated, but the vapors obtained due to burning of the fuel touches the ore in the hearth and heat it. Retort furnace. In this furnace, there is no direct contact between the hearth or firebox and even the flames do not touch the ore.